All right, number 35 is going to be the bonus problem on your test. I'll tell you right now, a little hint for you if you're watching this video. However, number 35 is not the bonus problem in your review guide. You still have to do it on the review guide, and then it will be bonus on your test. Solve the following systems algebraically and graph the systems to show their correct intersection points. Let's start with the graph. Let's start with graphing. Part A here we're going to focus on. This graph is just the mother function normal parabola. That means that his vertex, you can imagine it, is +0 and then +0. My vertex is 0, 0. And if I plug in some points to see where the other points will be, I plug in like 1 and 2, I get 1 and 4. So I can already graph this original parabola. I'm going to do that in blue. I'm at 0, 0 for my vertex, and then I'm at 1, 1, and symmetry, -1, 1, and then I'm going to go over 2, up 4. And I'm going to do the same thing on the left side. If you want, you could even plug in a 3. Well, what's 3 squared? It's just 9, so over 3, up 9. 9 is right there, which means it's right here. Okay, so there's my parabola. I'm going to connect this as best I can with my blue points in like a curved kind of fashion. Something like that, and then maybe like that. Okay, now let's go ahead and let's graph this line. I have y equals mx plus b, so that means my b, or my y-intercept, is going to start at -1, and then my m is 2 over 1, so up 2 to the right 1. If I go up 1, 2 over 1, oh my goodness, I'm right there on an intersection point for sure. I totally just found an intersection point right there. Awesome. Let's keep graphing this line just to see if there's another one. Up 2 over 1. This might be an intersection point. Do you guys see this right here? But I'm not sure if this parabola actually hits that lattice point or not. And then up 2 over 1, I'm definitely not going to hit that parabola again. My line is kind of going off to the side there. So let me go ahead and connect these dots the best I can. Again, I know for sure I have an intersection point there. I'm not quite sure if there's one there or not. That's why graphing is kind of hard, because you can't really tell if you have intersections or not. Let's go ahead and solve this algebraically as well to see for sure if there's 2 intersection points or just 1. The way we solve algebraically is we take our 2 equations, which again are just this, and we're going to solve using substitution. So that means I know what y is. Y is x squared, so let's substitute the x squared in for this other y over here. Okay, well, y equals x squared, so instead of writing y, I'm going to write x squared, what he equals. So I basically just created this problem, which is going to be a quadratic that can be solved using, say, like the quadratic formula. If I can get all of one of these sides to be 0, then I could use like the quadratic formula. My goal here, I think what I'm going to do is try to make this side be 0, just so I keep my x squared positive. I don't know, I always like to keep my x squared positive. So I'm going to move the 2x over and the 1 over. In other words, I'm going to subtract 2x from both sides, and I don't have anybody to subtract him from, so I'm just going to literally just write him behind. And then I'm also going to add 1 to both sides. And I don't have any like terms, so I'm just going to write him behind. And now you can see I've got this situation going on, which is going to be either factorable, complete the squareable, or you could use quadratic formula. I'm going to do a quadratic formula here just because I know that it works every single time. So the a is the number in front of x squared, which is 1. My b is -2, and my c is 1. If x equals negative b, so -2, there's my b, plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So out front I have x equals 2 plus or minus the square root of -2 squared, well that's 4, minus basically 4 all over 2. Well, hold on. That means x equals 2 plus or minus the square root of 0 all over 2. Well, what is the square root of 0? It's just 0. So that means x equals 2 plus or minus 0 over 2. So, I mean, even if you add 0 or minus 0, it won't change anything. So that means that x equals 2 over 2, or x equals 1. Oh, totally. X absolutely equals 1. My x value of my intersection point is 1. What's the y value? How can I use algebra instead of the graph to show the y value? Well, let's just plug it in that x equals 1 to either one of these two equations. It doesn't matter which one you pick. If you do happen to pick this one, you would just do y equals, instead of saying x is 1, or x squared, you're going to say 1 because that's what we just solved x was. So y equals 1. Is my y value of the intersection point 1? It sure is. So I have 1, 1. That's my intersection point. The answer to this problem is 1, 1. For the next one, we have looks like a parabola and a straight line. This parabola is not ready to graph though. We need to turn that into vertex form to be able to get this guy ready to graph. Let's do a little scratch work below. I am going to show my work for graphing this parabola. I have y equals x squared minus 1x minus 2. So this is very similar to the problems in our, I think it was our second video, where we are converting to vertex form to graph the equation. I'm going to use completing the square to convert this to vertex form. In other words, I'm going to take the last value, add it to the other side of the equation, and then take a blank on both sides and fill it in. I fill that blank in by taking the middle term, dividing it by 2, which will give me negative 0.5, and then squaring that, which will give me 0.25. Okay, it's okay that you have fraction or decimals. It's going to work out. Now that means that on the left-hand side, I really have y plus 2.25 equals x squared minus 1x plus 0.25. If I go ahead and factor this using my square root of the front, square root of the back, sine of the middle thing, then the square root of the front gives me x. The square root of 0.25, if you don't know, use your calculator. It's just 0.5, and the sine of the middle is minus. Now, if I put this guy back over to the other side, I have y equals x minus 0.5 squared minus 2.25. Here is the vertex form of that first parabola. The importance of doing this is to realize that your vertex is going to be switch the sign, so 0.5, comma, leave the sign, negative 2.25. So let's go ahead and start by graphing that point. We have the vertex, so let's graph that point. Again, I need to go, my vertex point, I know I just moved from it, is 0.5, comma, negative 2.25. So 0.5 would be like 0.5 over, and then negative 2, 2.25 is like somewhere in the middle here. And just do your best. It's not going to be perfect, but it's somewhere in the middle of this dot right here. Okay? To find the rest of this parabola, we're just going to need to use an XY table. So if I use an XY table, say I plug in, well, we're at 0.5, so let's maybe try 1 and then maybe 2 and see what happens. If I plug in 1, I'm basically asking myself, what's 1 minus 0.5 squared minus 2.25? And guys, I'm just using the vertex form, which we just found down there, and I'm just plugging in 1. And when I do that, I get the value negative 2. So I plugged in 1, and I got negative 2, so it's right here. Let's go ahead and graph that point, which means he has a mirroring point right here, okay? And then if I plug in, say, let's try 2, so that would be 2 minus 0.5 squared minus 2.25, and that gives me 0. When I plug in 2, I get 0, so I'm right here, and then that means right there. So you can kind of see where your parabola is going. You can connect that using like a rounded line. And then finally, we're ready to graph our straight line, which is y equals m looks like it's a 1, x plus b, which is -6. Let's go down 6. 1, 2, 3, 4, 5, 6 right here. And then my slope is up 1 over 1 from there. So you can see that my line is starting to form. And no matter where I go with this line, am I ever going to hit that parabola? Look. They are so far apart from each other. There is no way this is going to cross. So that means the answer for this intersection, there is none. No solution. So since these guys don't cross, they don't have an intersection, so I don't even have to solve this algebraically. There are no real answers to that solution. Okay? Last but not least is part C. The good news about part C is this parabola is the exact same as this parabola. You already did that work. You don't need to do that work again. So steal this exact same picture for your first parabola there. I'm just going to steal it really fast. I have a vertex of 0.5, negative 2.25, and then we plugged in, what did we plug in? We plugged in 1, and we got negative 2. And then we plugged in 2 and we got 0. Again, this is the same one from part B. Okay, so I get this kind of looking parabola, maybe like that, and then maybe like this. I just stole the same graph because, again, it's the exact same thing. So that means I only have to do some work or some completing the square on this one. Let's scoot it over and do a little bit of work here. I'm going to complete the square on y equals x squared plus 2x plus 1. And to do that, I'm going to first start by subtracting 1 on both sides, which gives me y minus 1 equals x squared plus 2x. Let's add in those blanks, and let's fill in those blanks by dividing by 2 and then squaring. So I need to add 1 to both sides, which means I have, it looks like y, I don't know, plus 0, so just y, which is awesome, equals x squared plus 2x plus 1, so I can go ahead and factor this. The square root of the front is x, the square root of the back is 1, the sign of the middle is plus, and then I don't have to move anything over here. If you want to put a plus 0 to kind of signify, hey, here's your vertex. My vertex then is going to be switch the sign, negative 1, leave the sign 0. Here's the vertex of the next parabola. Negative 1, comma, 0. Oh, look, it's definitely an intersection point. We totally just found an intersection point right there, okay? Let's continue this red parabola just to see what he does from there. X, comma, y. I'm going to plug in some points. Right now, this red parabola has a vertex right here. So let's plug in points, I don't know, say like 0 and 1. If I plug in 0 and I'm using this equation, I'm going to do basically y is 0 plus 1 squared plus 0, which gives me 1 when I solve it. So that means 0, comma 1 right here. And then if I plug, oh, and then of course my mirroring point over here. If I plug in 1, I would have 1 plus 1 squared plus 0, which is, of course, 4. So that would give me 1 up 4 right here, and then his mirroring point right here. I'm not quite sure if this red guy is going to intercept that black guy again. I don't think he will. It kind of looks like the black parabola is going to stay inside of this red parabola because he's growing kind of fatter than the black one is. But how could we check to see if he is going to intercept or not? Well, let's solve this algebraically. In other words, let's set these two equations equal to each other to solve. I have the equation y equals x squared minus x minus 2, and the other equation y equals x squared plus 2x plus 1. Since I know what y equals, I'm going to plug in what y equals into the other equation. In other words, instead of writing y, I'm writing what y equals. X squared minus x minus 2. So that equals x squared plus 2x plus 1. Another way to think about it is y equals this and y equals this, so they must equal each other, okay? Now let's solve this equation. In other words, let's put them all on one side of the equal sign. Watch what happens. If I subtract x squared from the left to move him over to the right, well, these guys cancel, but so do these. So they're gone. They just completely disappeared, and I'm left with negative x minus 2 equals 2x plus 1. Take a look at this equation. It is no longer a quadratic. Your quadratic pieces, your x squared, just disappeared. So now, this is just a linear equation. You can solve this for x without using the quadratic formula, which is awesome. Let's solve this for x. I'm going to add x. That means I have negative 2 equals 3x plus 1. Again, I'm just solving for x here, so I'm going to subtract 1 on both sides. I have 3x equals negative 3. So if I divide both sides by 3, I have x equals negative 1. Well, let's see. Does that make sense in our graph? Does x equal negative 1 in our intersection point? Our intersection point looks like it might be, let's see, negative 1 comma 0. Yeah, x does equal negative 1 in that intersection point. Awesome, awesome, awesome. So then how do I check that this 0 is correct? Well, you plug in that x equals negative 1 into either one of these two equations. Let's plug it into this equation just to see what happens. Y equals, instead of writing x, I'm writing negative 1 because that's what we just found out x equals, minus negative 1 and then minus 2. This will give me 1, this will give me plus 1, and then this will give me minus 2. So that means y equals 2 minus 2, or y equals 0. Exactly what it's supposed to be. Y equals 0, x equals negative 1. You found your one and only intersection point for part C.